Modern researchers define a skyscraper as any multi-story building that reaches at least 100 meters in height. Structures taller than 300 meters are classified as super-tall skyscrapers, while those exceeding 600 meters are known as mega-tall skyscrapers. These giants of concrete and steel stand among humanity's greatest engineering achievements. Towering 828 meters over Dubai and with 163 floors above ground, the Burj Khalifa is the tallest building on Earth. For thousands of years, humans have tried to reach the sky, from pyramids and cathedrals to modern skyscrapers. Each era believed it was nearing the ultimate limit of height, yet time and again, new records were set. Before the first shovel touches the earth, engineers and scientists spend years analyzing invisible forces, those hidden beneath the soil, in the air, and inside the building materials. This is because a skyscraper is not merely a tall building, but rather a finely tuned scientific system designed to balance strength, stability, and safety. Every skyscraper begins with the ground upon which it will be built. Engineers must determine whether the soil can support millions of tons of weight. Soft clay, loose sand, or fill material usually compresses unevenly, causing the building to tilt at a dangerous angle or even sink, a process called settlement. Modern skyscrapers are engineered to minimize settlement by anchoring into strong layers. But even well-designed towers can experience tiny amounts of gradual settling over time, usually within safe limits. Skyscrapers don't actually sit directly on soft topsoil. Engineers dig deep below the loose upper layers until they reach firm ground or the bedrock. Steel or concrete piles are driven or drilled down into this strong layer, and the building's foundations transfer the load there. That way, the weight bypasses weak surface soils that would compress too easily. The type of soil, along with the height and design of the building, determines the tower's foundation. Soil samples are extracted and their load-bearing capacity is measured. If the soil is too weak to support the load, deep foundations such as piles or caissons are required. A similar foundation system was used in constructing the tallest building on Earth, the Burj Khalifa. Engineers used a deep piled raft foundation system consisting of a 3.7 meters thick raft supported by approximately 192 large board piles. Each pile was about 1.5 meters in diameter and approximately 50 meters in length. Both the raft and piles were cast using high-performance reinforced concrete. Unlike cities built on solid bedrock, Dubai sits on a weak sandy soil, mixed with limestone and groundwater rich in salts and sulfate. This was a major challenge to engineers because this type of environment is hostile to concrete and steel. It is capable of causing long-term corrosion and structural failure if not carefully and properly managed. To stop the destruction, engineers used electricity as a part of a cathodic protection system to prevent rust and corrosion in their reinforced concrete piles and rafts. A controlled electrical current is applied to the steel through installed anodes, making the reinforcement act as a cathode. This electrical process suppresses the electrochemical reactions which causes rust, significantly slowing corrosion and extending the structural life of the foundation. After 6 years, the Burj Khalifa was standing tall. Now, the biggest enemies of any skyscraper are natural unseen forces. Gravity is the most obvious force, yet also the most dangerous. Every column, beam, and bolt carries the weight of everything above it, permanently. If the concrete is not strong enough, it slowly deforms under constant load, shortening floors and redistributing stress. If part of the foundation sinks unevenly, the building begins to tilt or crack. Wind does not just push, it oscillates. At great heights, wind doesn't push steadily. It gusts, changes direction, and creates vortices, which apply fluctuating forces to the structure. If a skyscraper were stiff and unable to move, wind forces would concentrate at weak points. Building materials would fatigue and crack faster, causing structural failure to occur suddenly. Therefore, engineers intentionally design skyscrapers to sway. Engineers equip skyscrapers with a special vibration control system called a tuned mass damper. A tuned mass damper is used in skyscrapers to reduce swaying caused by wind, earthquakes, or other dynamic forces. It is a very large heavy mass, often weighing hundreds or even thousands of tons, installed near the top of a skyscraper. It is designed to move in the opposite direction of the building's motion, cancelling out vibrations and making the building more stable. This opposite motion reduces sway by up to 40 to 50%. A small controlled amount of movement actually protects the building and the people inside it. A perfectly rigid skyscraper would be far more dangerous. By allowing them to sway, the buildings absorb and dissipate wind energy instead of resisting it outright. Movement spreads forces throughout the frame rather than locking them into columns and joints. The following is a clear example. A rigid tree snaps in a storm. A flexible tree bends and survives. Skyscrapers follow the same principle. Controlled flexibility reduces cracking in concrete, prevents steel fatigue, and extends the building's lifespan. During an earthquake, the ground moves violently beneath the building. If the structure were rigid, ground motion would be transmitted directly upward. Floors could shear apart, and collapse risk would skyrocket. Instead, skyscrapers are designed to move with the ground, allowing the shaking energy to be absorbed and released safely.